I will let Daniel Whiteson introduce his student. For those who are wondering who then Daniel Whiteson is, well, he is a Rice alum, class 97. Okay, wait. I have a bit of an echo here. Sorry about that. What I was going to say is some of you know Daniel because he wrote a book a few years ago saying that we have no idea. I think actually, Daniel, you talked about the fact that you have no idea here for the graduate students a couple of years ago, if I'm not mistaken, right? So anyways, I will let Daniel introduce his student, Taylor. Be mindful of Taylor. He is in a different time zone, so is Daniel, but they really are in very different time zones themselves. Taylor right now is in France, in Clermont-Ferrand, and Daniel is in California. A few hours this way, a few hours that way. So Daniel, why don't you introduce your student, and then we get this seminar on the way.
All right. Hello, everyone. Thanks, Frank, for the introduction to the introduction. So I'm Daniel. I'm a professor at UC Irvine, and I'm very pleased today that you have chosen to come to this presentation by my sharp student, Taylor. Taylor and I have been working for a couple of years with Jesse Thaler and other folks on answering the question of how to interpret deep networks. Taylor's done an amazing job here. Really, I think, created something which will help guide the future of understanding what deep networks are doing. And the reason you're hearing about this work from Taylor is because Taylor did most of the work, and so he's the best qualified to answer your questions. Please pay attention and ask him questions. He's introducing a lot of stuff which you probably haven't seen before, and so please feel free to chime in. Our goal is that you understand his talk about understandable networks.
Thank you for the introduction. I'm probably going to stop my video, so I don't know how good my internet connection is here. But yeah, so it is very helpful for me if you ask questions sort of during, if something doesn't make sense, because it's not ever necessarily clear when I'm not explaining something well. So feel free to ask. But yeah, so this talk is based on a paper that we put on arXiv and we're putting on Physics Review D right now about trying to understand how to interpret sort of things like deep neural networks and other black box machine learning tools. When they learn information, how can we learn what information they've learned and then apply that to the physics that it's supposedly learning. So my first slide is sort of the collaborators. So myself and Daniel are at UC Irvine, and Jesse Thaler, as was pointed out, is kind of the theorist that we are in contact with for this paper. And he's out of MIT. And then based on the material, sort of the machines are kind of our co-collaborators in what we're trying to learn. So I think the easiest way to understand what our motivation is for this project is to introduce kind of an interesting machine learning problem that we came across in the area of jet physics. So as I'm sure you're aware, we generate large amounts of data. One example is at the LHC. So the four main experiments, ATLAS, CMS, LHCb, and ALICE, we tend to generate something like 25 gigabytes of data every second during run times. And machine learning is a kind of obvious, convenient tool for dealing with these kind of large data problems. And it doesn't just get used in things like classification tasks, which is sort of the obvious kind of bread and butter situations for big data. But if you look on the arXiv, what you'll find is that everywhere from simulation to triggering to event reconstruction to even things like designing future detectors, machine learning tools are being applied to those kind of fields. And there's something like 1,000 new machine learning related papers put on arXiv every month. So this is a really hot field for research, and we're constantly introducing existing machine learning tools into the high energy kind of pipeline. But one of the big issues with constantly using ever increasingly complex machine learning tools is that most of these tools are what get referred to as black box methods. So we have, say in the case of a classifier, we're feeding input into something like a deep neural net or a convolutional neural net. And then we out from that machine learning algorithm or tool, we get some kind of prediction, but we can't really inspect what the black box learned. There's no obvious or easy method to sort of map a simple function from a black box. So all these different tools that were those thousands of papers on arXiv a month, most of those are kind of these black box methods where when they learn something, it's not necessarily obvious what they've learned or what information is being accessed by the deep neural nets or the adversarial neural networks or whatever you're using. It's just kind of this mysterious function that maps inputs to predictions. So they're very powerful, but you might ask, well, why is it a problem? Why can't we just use these black box methods that give good predictions on inputs, even if we don't understand how they're doing it or what it's doing? So one real world scenario where we came across a problem with using something like a black box is a situation of trying to design a jet classifier. So when you collide protons together, one of the things that you'll generate a lot of is these quarks and gluons that hadronize into these collimated sprays of particles, which we call jets. And a standard sort of procedure of analyzing jets is that you'll try to reduce the dimensionality of your data. So you'll collect raw data of jets in your detector, and then you'll go through this increasing process of sparsifying your data, reconstruction, selecting sort of subsets of the data. And ultimately, what usually you'll have is something like a jet substructure observable that you want to try to learn whatever your prediction task is. So two common types of reduced data set that you'll see in something like a jet classification problem is, one of them is these high-level jet substructure observables that I mentioned. So something like jet mass or end subjettiness is a common one if you're trying to learn the number of prongs, say, of a dijet sample. Another way that you can sort of parameterize your data is to treat it kind of like it's an image. So we have all these really powerful tools in image classifiers. So things like convolutional neural nets. And a more recent idea is to try and apply something like a convolutional neural net to a jet image where you're treating the energy depositions in your calorimeter essentially like it's pixels in an image. And so you can try to do things like convolutions on these jet images and try to learn the problem that way. And these are two popular sort of reduced dimensionality formats of a jet. And so a question we asked was, well, which version of the data is a better format for learning a simple classification problem? So the high-level jet substructure is something that is sort of using physics-motivated information, whereas a jet image is kind of treating treating the data like it's a photograph, and then just asking something like a convolutional neural net to learn the distribution of the energy in your calorimeter. And so we asked the question, well, I'll go ahead.
Sorry, I have a question about the definitions of these two versions. So how do you define the dimensionality here? Like,
so
are these the number of, you can say, the free parameters in all of these, or what is
it's
that?
essentially the size of your input. So say, for example, in the case of a jet image, our jet is, the image is basically a 32 by 32 grid. So like a 32 by 32 pixel image. So the dimensionality of that is 32 times 32, so what, 1024? Whereas in the case of something like jet substructure, these are very simple one-dimensional inputs. So if it takes 10 jet substructure observables to learn the problem, then your dimension is essentially just those 10 features.
Okay, thanks.
Yeah, so the high level is an even farther reduced data set. It's sort of the minimum, the most reduced version of the data is a couple of simple 1D inputs. So we asked the question, well, which of these two sort of works better? Is it the physics motivated observables like jet mass and ends of jettiness, or is it kind of the machine learning approach where you treat your jet information like a photo and ask a convolutional neural net to learn the problem? And the specific classifier that we decided to try this on is a monojet versus a boosted dijet. So in the case of a boosted dijet, you get this interesting feature where as you increase the momentum of your jet, your two jets start to overlap. And this becomes a more difficult classifier of trying to learn a monojet from a dijet. Because essentially as if you have this W that decays to two jets, the more boosted that is, the more they overlap and the more your pairs of jets start to look like a single jet. And so this makes for kind of an interesting, difficult image classification problem. So we trained a convolutional neural net to try to understand the difference between these two examples. And what we found is that, in fact, the convolutional neural net does outperform just the physics-motivated observables. And it does so in sort of a statistically significant amount. So the ROC curve and the area under the curve of your ROC curve is a metric for how well your neural network is performing. In the case of a CNN, looking at jet images, you end up with a small but statistically significant improvement over just using sort of the standard jet observables. And so the next question we had was, well, what is this extra information? We had 6 substructure observables that we were using. So the obvious question is, well, maybe there's a 7th observable or an 8th observable or some extra information that we could supplement what we have currently. And then you could make up this information to understand what is the convolutional neural net learning that we didn't have in our jet substructure. But the problem, as I mentioned, is we're using black box methods for this. So a convolutional neural net and a deep neural net is essentially a black box. And so there's no obvious way that we can understand what the CNN is learning that isn't in the deep neural net or the boosted decision tree with jet substructure.
I have another question.
Sure.
So in this study that you are showing here, I assume that from the previous slide that the signal is, let's say, the WW or the jet coming from the W, and the background is the QCD jet, right?
Yeah, that's right.
Okay, but in more, let's say, going into more specific problem of let's say comparing the W plus jets kind of process with the WW kind of process, where you have a mixture of jets, let's say, coming from W and also from the hadronic activity or QCD, and in the case of, let's say, the WW process, you have definitely the jets are coming from the W. Have you considered other possibilities of backgrounds instead of QCD jets only in this study?
For this study, we didn't. So the main, so this study right here is actually a previous paper that some other members of our group had worked on.
Okay.
And so for our follow-up paper, the reason that we started with this data set is that we knew that there was this existing gap in information between the low level and our high level data set. So the other paper potentially could have looked at sort of other backgrounds, but we specifically wanted to use this signal and background data set.
Yeah, I mean, this is the most common, you can say. I mean, that's fine. And have you also studied the flavor, the different jet flavors, for example, in this? That if you can identify the flavor of the jet more better than, let's say, the usual identifiers of the flavors, let's say.
So we have some other work going on that does essentially that kind of search.
Okay.
And I can, yeah.
Okay. Thanks.
Yeah. So, but yeah. So in this sort of monojet dijet example, we have this case where we have a black box that's learned extra information, and we don't really know how to get access to that extra information. And so that's sort of an obvious problem if we don't know where information comes from, or rather what physical significance the extra information has in this other machine learning approach.
And can I ask something?
Sure.
So if you go back, so when you have this jet classification, I mean, you in principle, in your sample, you can look energy, invariant mass, etc., right? And then you can infer what the machine is learning, right? Based on those distributions. So it is learning something, right? Because you can plot all of these physics variables like the transfer moment or energy in the calorimetry, and then you can see how the machine is classifying these jets based on those physics observables, right? The thing is that information is already encoded in your pixel matrix somehow, right? That's the way that I see this.
So you can look at the 1D observables. That doesn't necessarily mean you can understand how, say, a boosted decision tree is using that information.
What?
But and also, so the information is in some way encoded into the pixels of the jet images. And then the fact that there appears to be more information in the jet images than there is in the jet substructure suggests that there might be some additional jet substructure observable we would want to look for.
So yes, I agree with that. And I think the reason to be is that the dimension, if we are at the level that we can not do any more one-dimensional codes for analysis in high-energy physics. So by looking into this 3x2 pixel matrix, you encode more information because this is now a multi-dimensional analysis, right? As opposed to one single linear code in every single 1D distribution.
But essentially what we find, and so I'll show this later on in the slides, but we are able to find another 1D observable that when you include it, it gives you the same performance as the jet image. So it turns out you can add one more jet substructure observable and then get the same performance.
Okay, I would wait.
So it's not necessarily just an improvement just because of the dimensionality. So some additional problems just beyond the fact that we're using a black box and we don't really understand or know the physical significance of this missing information. It becomes difficult or even impossible to sort of validate your data or do things like measure systematic uncertainties on your data sets for something like a jet image. That's a possibility with 1D observables. You can sort of plot your histograms of invariant mass or end subjettiness and make corrections. That's not really something you can do easily or at all with something like a jet image. And then there's also some obvious practical kind of pragmatic issues of jet images are just much larger. The larger the dimension of your data, the more storage it requires, the more memory it requires when training, the more intensive the training usually has to be in order to kind of suss out useful data. So all of these things combined make it a really tantalizing prospect to be able to encode the same amount of performance that you get from something like a black box into a really simple neural network or machine learning approach that uses only 1D observables that you can understand in terms of the physics. So this is our motivation, and a couple of slides here show that this is a very common problem. So it's not just this dijet monojet case. We have a couple other papers where we look at, for example, a Higgs classifier. So you have these, again, it's a signal and background, but now it's two different Higgs processes. And we have sort of an equivalent high-level and low-level version of our data. So in the low-level case, we're mainly looking at things like jet PT and different kinematics, so missing transverse energy. And then there's a high-level version, which is the different invariant masses of kind of the sub-processes of our two Higgs processes. And you see the same sort of gap in the high level and the low level, where the low level version of the data performs much better than the high level. Or there's another paper we did where we look at electron classifier, and it's the same sort of large gap in the low level version of the data outperforms the high level pretty significantly. So it would be convenient if we had kind of a one size fits all method of translating from something like low level to high level that we could apply to any of these different situations. So that's essentially what we tried to do. And this is how we try to solve the problem. And there's a few different ways that you can approach this kind of problem of having a low level and a high level method where the low level outperforms. So one of them is just to ignore the low level version. So to commit to only using sort of interpretable models. And this is kind of not ideal for obvious reasons, being that you just lose all the performance that you would have gained for using sort of more modern techniques. So all the different advances that people have made in big data analysis, you just have to ignore if you want to commit to only using interpretable models. Another approach that some people have made is to take something like a black box deep neural net and then sort of modify it in interesting ways to make portions of it interpretable so that you kind of get the benefits of a more complex deep neural net, but then there's sort of sections in which they're interpretable and you can try to understand them. And one example I give is Microsoft Research has some interesting papers about how they apply sort of this approach to different healthcare learning models. The third version is essentially what we try to do. So in our approach, we're going to just use the black box, so something like a deep neural net or a support vector machine. And then once you've learned the information with those black box methods, we're going to apply a method to then sort of translate the learned information into a space that we can understand and interpret. And so there's two main advantages to this. The first being that however much performance you can get out of your data with whatever method you want to use, you can go ahead and just use all of that performance. You don't have to sort of lose training performance at the expense of interpretability. And the other is that you can use any model or training method that you want. So if a deep neural net seems to do the best on your problem, then you can use that. If a boosted decision tree or in other examples that we've looked at, things like particle flow networks or energy flow networks, if they outperform all other methods, you can use those. And so it's kind of a one size fits all approach. And there's essentially three parts to our approach that are necessary. So one of those is we need some kind of low-level black box method. So in our case, in say the dijet monojet problem, the low-level convolutional neural net on jet images that's kind of our low-level solution. And this is where the information that we're interested in exists, but it's just inaccessible. The second part is we need some kind of human readable or interpretable space where we can map that low-level solution into, so that whatever information is there that we don't know about, we can map it into the human readable space. And then the third component is that metric that's going to tell us where in our human readable space we should be looking for that information. And so these three components essentially is all you need in order to try to read interpretable information from a black box neural network, or at least that's what we are claiming. So the second piece, if the first piece is our low-level jet images, the second piece, which is our human readable space, in jet physics, so a good candidate for that is a thing called energy flow polynomials. So EFPs are this infinite space of 1D observables, so things very similar to, for example, n sub jettiness or jet mass. But it's this infinite space that completely spans the entire jet substructure basis. So any information that exists as a jet substructure observable, in principle, should exist as an energy flow polynomial. And in fact, in the formulation of EFPs, things like energy correlation variables, or invariant jet mass, or PTD, these all exist as EFPs in the EFP space. And the way that EFPs are defined is any graph you can make with any number of nodes or edges, this infinite space of graphs that you can generate, each of these is an energy flow polynomial. And then each graph you can make, the node of your graph tells you how many summations you're going to do over the fractional momentum of the constituents of your jet, and the edges of your graphs are the angular separation between the constituents. So something like invariant or energy correlation is already kind of these sums over partial momentum. And so the energy flow or energy correlation exists as an energy flow polynomial. And you can have very simple energy flow polynomials. So say 2 nodes with a single edge. And then you can have these really complicated EFPs where you're doing multiple summations over your constituents with different weightings on either the separation of your constituents or the fraction of momentum of your constituents. So for every EFP, you also have these kappa and beta parameters that act as sort of weights or emphasis on either your momentum or your angular separation. And so this is kind of our human readable space. When we pick an EFP as a useful EFP, the fact what kappas and betas it has, or how many nodes and edges, gives us information about either the angular separation, the significance of something like the angular separation in our observable, or the significance of, say, the distribution of the energy in the jet image. And so the third piece is we need now some metric basically to map between the low level and these EFPs where we can kind of interpret the information. And when we first approached this, our initial thought was, well, maybe you could just use something like a rock curve and the area under the curve for a rock curve. So if I train a low-level neural network and I train a high-level neural network, maybe if I just look at the rock curve of those two and they have the same performance, then I can conclude that sort of that those two networks are actually making the same, or are using the same information. And what we essentially realized is that it's very common that two neural networks can have the same or similar performance, but they're actually solving the problem in different ways. So what we ended up having to do is come up with our own kind of custom metric that doesn't just look at how well do two neural networks perform, but are they actually making the same decisions? So the question we really want to know is if we train a convolutional neural net on jet images, how do we know when it's using the inputs the same way as, say, a boosted decision tree? And so rather than a ROC curve, we invented this metric that we call the average decision ordering. And this, I think this part is probably the part that's the most confusing part. So feel free to ask lots of questions in this section. But the concept for the decision ordering is, in something like a ROC curve, what you're essentially doing is you're looking at your false positives, and at every sort of threshold of your false positive rate, you're asking the question, well, what is the true positive rate in that section? And then you slice through your false positives, constantly recalculating the true positive rate. What we instead want to do is the same kind of approach, but rather than false positive threshold and then measuring true positive rates as we sort of move through that threshold, what we're essentially doing is looking at the decision boundary. And as we move the decision boundary through that space, we want to measure whether or not our outputs have the same decisions or not. And so the way that we accomplish this is from our data set, what we do is we take random signal and background pairs. And then we ask the question for each of our two neural networks, so F and G, if this is like our low level and our high level, we ask the question, does the high level and the low level map the randomly selected signal and background in the same way, or does it map them differently? So for example, if the high level takes two events, a signal and a background, and maps them, the signal to signal and the background to background, and the low level does the same mapping of that same input from signal to signal and background to background, then we consider that a similar ordering. Or alternatively, you could have the opposite where they both map a signal to background and a background to signal. And in both those cases, even if the neural networks are making the wrong choice and mapping a signal to a background, the question we really want to know is, did they make the same decision? Because really what we want to know is, does the decision surface of those two neural networks make the same decision with the same set of inputs? And the alternative is you can have dissimilar orderings where, say, the high level takes a signal to a signal and maps a background to a background, but the low level makes an opposite choice and thinks that that set of inputs is the opposite prediction. And so what we do is we take those randomly selected signal background pairs and we look at millions of them. So we just repeatedly take pairs of signals and backgrounds, and we ask the question, do the low level and high level make the same mappings or different mappings in their predictions? And then we calculate the average over sort of many examples. And in that way, we're looking at, for millions of events, how did the two decision surfaces map all those different inputs? And in the end, that average tells us how similar the two decision surfaces of those two neural networks are. And what you end up finding, or what we end up finding, is what we expected, which is that the two neural networks can have similar performance. So for example, these are examples of deep neural nets training with just individual observables. What you end up finding is that two observables might have similar performance. So say this energy correlation variable and subjectiness here, they end up with the same or almost the same AUC, but they're actually they have very different decision surfaces, the two neural networks trained with those. So they make very different choices with the inputs, despite having sort of similar performance. And this is our metric that we're going to use in order to tell us when we have information from the low-level space, where in the high-level space do we get something like an energy flow polynomial that has a similar decision surface. So I think it might be a good idea to stop if there's any questions for this specific part. Okay, so if there's not any questions, so now we can kind of move on to the algorithm that now makes use of these three components. So like I said, we need a low-level space, a high-level space, and then kind of a metric to map between them. So the specific algorithm that we use is a process where we're going to sort of iteratively add new EFPs every time to try to build up a set of just 1D observables. And so we start off by just training a simple deep neural net, so sort of a fully connected deep neural net of just high-level observables.
Actually, can I ask a question right here?
Yes.
Could you achieve the same thing by just training a series of nets on your EFPs?
Yeah, so towards the end, we'll give an example where we kind of ask a similar question, which is, maybe you could just train neural networks with lots of EFPs.
Right.
And and so we kind of call this our brute force approach, where you're not really sure which EFPs are the best ones. So you just try all of them, either one at a time, or try all of them in like one big group.
Right.
And basically, not to spoil the ending, but what you find is that you could do that. It just is very inefficient way of doing it.
Okay. That makes sense.
Yeah.
But in principle, you can learn which EFP is the best, right? And because this is a graph at the end, you can learn what is the best graph. Probably you go to the stream to have a very dense graph or very sparse graph, but you can find something in between, you learning from the data, right?
Right. And so, yeah, so because our motivation is in large part that we want to understand what information the CNN learned, what we really want to do is be very careful about which EFPs we pick. And so if we can pick just say one or two EFPs, that'll tell us something useful about what information we're gaining. Whereas if we just sort of
But you can bias a little bit the CNN, right? By limiting, by whether you're using a very sparse or very dense EFP, right? I guess, this is just an approach, right? But naively, you will assume that you will scope the result of the CNN because of this, right?
Yeah.
Okay. Yeah, I'm just trying to understand exactly what you're doing.
Okay, yeah. Yeah. So for our algorithm, so our first step, we sort of train a neural network with just our normal, with the high-level observables we already have access to. So this is the things like invariant mass and subjettiness. And then what we do is we generate a random set of signal background pairs that we're going to look at the decision ordering of. And from this random set of pairs, what we do is look at which of these pairs have similar orderings between the low level and the high level, and which ones have dissimilar orderings. And because what we want to do is we want to isolate just the pairs where the low level and the high level disagree about the orderings. So we're kind of slicing out a subset of the latent space where the low level and the high level are in disagreement about how the decision surfaces should map those values. And in that space where the high level and the low level disagree, we want to then find an EFP that makes decisions most similar to the low level. So in the region where the high level is doing a very poor job of mimicking the CNN, we want to find an EFP, so this nice 1D observable that does a much better job of mimicking those decisions. And once we find sort of that EFP that does the best job of mimicking the low level in this differently ordered subspace, we're going to include that as one of our new observables. And then essentially go back to the beginning and start over. So train a new high-level neural net, now including this EFP that does a better job of filling in the information that the previous high level did a bad job at. And we're going to re-ask the question now in this new space, with this additional EFP, what's the new subset of information where the high level and the low level disagree. And in this new subspace, we want to add now another EFP that might do a better job of filling in the gaps where the previous high level didn't. And we can keep repeating this process until either we've completely matched the decision-making of the CNN, or we have the same level of performance, but now we have the same level of performance, but with just sort of physically interpretable observables. And so this is kind of my little cartoon explanation of that process. So if you kind of think about the CNN and the DNN, they essentially make similar decisions in most of the space because they already are getting kind of comparable performance, so they have to be making sort of similar decisions. But because they are making different decisions in sort of a subspace of it, essentially we're trying to take that subspace, this little subsection of the latent space, and where it does poorly, we want to find an EFP where that does well. And then when we include that EFP in there, a deep neural net should be able to take that EFP and learn information for that subspace or that subsection of the data that's useful and makes similar decisions where the low level was doing a good job. And then we want to just keep repeating this process each time, filling in this sort of differently ordered subspace. So if we do that, and we tried this with the dijet monojet case, you can ask the question, well, how many EFPs do we need to add in to recover the information? Well, so it turns out for that one, it just took one EFP. So we only had to run this algorithm one time. And the first EFP it suggested, it turned out gets within sort of the statistical uncertainty, it gets the same AUC. So we're getting the same performance as the CNN now with our original high level plus one extra EFP. And we can ask the question, well, what is that EFP that it picked and what information does it tell us? So it's this graph with the parameters kappa equals 2 and beta equals 1/2. So this graph, some details about it. So for one, any EFP, anytime you set your kappa value to anything other than 1, that makes that EFP an infrared and collinear unsafe observable. So we tend to choose jet substructure observables that are infrared safe and collinear safe, because in the case that you have sort of these soft emissions that you can't account for in the data, it's convenient to have an observable that's kind of invariant to that. And same thing with sort of collinear. So along the axis of momentum, any kind of emissions that are sort of undetectable there, if the observable is sort of invariant to those kind of changes, then we think it should be useful to, that's sort of a useful feature for an observable. It turns out this EFP that the algorithm selected is not IR unsafe or collinear unsafe. Or sorry, it's not IR safe or collinear safe. The fact that it's a beta equals 1/2, so the beta parameter again is the angular separation, it's the weighting on the angular separation. So the fact that it's beta equals 1/2 suggests that it's sort of probing small angle behavior in the jet image. And then each of these graphs, sorry, go ahead.
Yeah, can you remind me what you mean by small angle? So this is the angle with respect to what?
So it's the angular separation of, in the case of jet images, it's the angular separation of the pixels. So it's essentially saying that the separation between, say, neighboring pixels, this EFP is more sensitive to sort of that fine-grained detail between between pixels that are closer together, as opposed to the information in pixels that are spread out from farther from one another.
But I mean, this has to be with the direction of the jets, basically, right?
Yes.
So yeah, just trying to understand. So, but we know that CNNs are invariant to rotations and translate and to rotations, so they don't have any information about angle, right? So that's basically what you're inferring from this EPS, right?
I'm not sure. So I don't think it relates necessarily to the rotational invariance.
Okay.
It's really a distance measure.
Yeah, so it's a distance measure between, in the case of jet images, it's the distance measure between the pixels in your jet.
Oh, so it's not so then basically what we're getting is that because this seems to be in some cases sparse data, the graph works better with sparse data than a CNN, right? Because
so it tends to be very sparse data, but what we'll see in a couple slides later is that it's often the case that it will pick EFPs with a larger beta. So it's probing wider angle behavior.
yeah, I'm confused about this angle, but go ahead, sorry.
Well, so essentially one way you can think about the difference between the sort of wide angle and small angle behavior is because we're looking at these dijets that are boosted, and so they're overlapping, it sort of suggests that what the neural network is benefiting from is looking very closely at neighboring pixels and trying to distinguish between, say, jets overlapping very close to one another. Whereas if it was, say, beta equals 2, that might instead suggest that what it's actually doing is it's looking more at how far separated out pixels are, and it's benefiting more from that information, from pixels being sort of spread out more.
But I have to say, I find this intuitively correct, because we know in jet physics, we're always sort of ignoring all this non-infrared safe stuff, but it's there. I mean, that's what really physically is going on, right?
Yeah, so it's all, I mean, it's there, and we're largely
we try to ignore it because it's inconvenient.
Yeah,
map,
it's inconvenient.
Right? So it's hard to get from jet level to parton level when you include that stuff. But the fact is that physics is going on.
Right. And so, and the fact that it it's selecting, so when you take the physicist out of the equation and you just ask this algorithm to pick an EFP, it is kind of interesting, but a little bit intuitive that it would pick something that is infrared unsafe or collinear unsafe, because that information could be potentially useful. And the reason we're picking it, like you said, is more out of convenience rather than just like raw machine learning performance.
It just makes the theory connecting to parton level easier.
Right.
Yeah.
And then, so one other thing about this graph, so each of these graphs has a property called it's a chromatic number. And one of the features of the chromatic number is that the chromatic number -1 is essentially how sensitive that graph is to the number of prongs in your jet. So for example, in this case, this is a chromatic number 3 graph. And essentially what that tells you is that this graph is more sensitive to 2-prong jets, which kind of makes sense because the problem we're trying to solve is a dijet problem. So it's picked an energy flow polynomial that is kind of more sensitive to learning a 2-prong jet problem. And then, so at the bottom, this is a histogram of the distribution of our EFP. And one thing that's kind of interesting is, so you get this nice signal background separation in the EFP. This one on the right is after you'd look at just the differently ordered subspace. And it kind of makes sense when you look at the signal background separation that these would be the events where 2 neural networks potentially disagree a lot about what's the sort of best way to map the signal and background pairs. And it's interesting, so even though you don't have a very distinct signal and background separation, there is information in there that's useful for something like a deep neural net to use to then improve and get this higher AUC that matches the convolutional neural net. So that's kind of a nice result. So we can start with our existing high-level observables and then add one EFP. We had sort of a second question, or a follow-up interesting question, which is, so you can start with existing jet substructure, but what if you just ask this algorithm to pick all the EFPs, or rather to pick all the observables for you from the EFP space? So kind of start with the minimum set of physics information, and then let the algorithm tell you which EFPs it thinks best fills out the rest of this data. And so we did this starting with, the only information that we started with is the jet mass, so the invariant jet mass. And then you kind of have to include the jet PT as a way for the energy flow polynomials. You need sort of a reference so that the neural network knows some scale for the EFPs. But starting with just those two things, we repeatedly ran this guided algorithm. And each time it picked a new EFP, and each time that EFP added useful information so that the deep neural net improved every time. And by the seventh pass, or rather the seventh EFP that we tried to add, we had reached the same performance that the CNN had learned, and also the same performance that the 6 high level plus 1 extra EFP had learned.
How was the order chosen of how these got added in?
So it's just chosen in so the algorithm each time, it's looking for which EFP is does the best job in that differently ordered subspace. Yeah, and so then we add that EFP and we just run the process again.
I just find it odd that charming, let's say, that the thing we try to avoid with all this infrared safeness is the thing that came in first.
Right, and so not only did the previous algorithm where we just picked one EFP, that was infrared and collinear unsafe. Essentially all of these graphs, nearly all of these graphs, are also IRC unsafe. So the first EFP it picks is kappa equals 2, so that's IRC unsafe. This one, kappa equals 0 also. You don't get an infrared safe EFP until number 4, and then number 6. So yeah, of the 7 EFPs it took to regain the same level of performance, 5 of them are IRC unsafe. And so we can kind of go through a couple of these graphs to see what information we learned.
Sorry, for those that we are not familiar with collider physics, can you just please explain what is this infrared safeness?
Yeah, so an observable is infrared safe if it's in a process, if there's sort of a soft photon emission. A soft photon emission is something that's not really detectable. And so if it happens, there's no way to account for it in your model. And so if you explicitly only use observables that are invariant to those soft emissions, then you just don't have to worry about the fact that you can't account for changes in your data due to something like a soft emission. And then in the case of collinear safety, it's the same sort of invariance, but with respect to kind of, I think it's gluon, like gluons that are down the sort of the direction of momentum. So you also really can't account for this collinear emissions. And if your observable is invariant to those collinear emissions, then it's not a problem that you have to deal with.
Okay, thank you.
Yeah. But yeah, so this process picks observables that are not invariant to those IR emissions and collinear safety emissions 5 out of the 7 times. And so some other features of the graph. So in addition to it being IRC unsafe, so it's a chromatic number 2 graph, which, as I said, so the chromatic number -1 is the sensitivity to the number of prongs. So this is the first graph is sensitive to sort of monojets. And it's similar, so jet mass is, there's an EFP representation of jet mass, and jet mass is a chromatic number 2 graph, but unlike jet mass, this first one it selects is a much more complicated graph. So whereas jet mass is a 2-point correlator, so 2 nodes with a single edge, this is a much more complicated sort of 5-node graph. And then beta equals 1/2 is, again, it's that angular separation. So this one also seems to be probing kind of small angle information in the jet image. The second EFP, though, it picks is actually the opposite. So now we start to get, for example, a beta equals 2, so a wide angle behavior graph. But it's also a chromatic number 2 graph, so it also is probing 1-prong substructure rather than something like 2-prong. And kind of an interesting feature of the 1-prong and 2-prong, or the chromatic number, is for most of these EFPs, it's picking chromatic number 2 graphs, and you don't get anything other than a chromatic number 2 graph until the 6th EFP, this one. So essentially, every time it's picking an EFP, it's picking EFPs that are sensitive to a monojet solution rather than, say, a dijet solution, which is interesting given that what we're really trying to learn is how to distinguish dijets from monojets. And when it eventually does pick something that's not either chromatic number 1 or 2, it picks a chromatic number 4. So it picks an EFP that's not actually sensitive. It's picking something that's sensitive to 3-prong jets for some reason. The third pass-through, so this single dot graph, this one's kind of interesting because it's an existing EFP, or it's an existing observable that we know about, but we didn't use in our previous studies, which is jet multiplicity. So this algorithm naturally just selected jet multiplicity as something useful without us thinking to add it in from the beginning. And we can kind of keep going through, but those are sort of the interesting features of these EFPs. But the overriding interesting feature of this study is really just how unconventional the EFPs are. So most of them are IRC unsafe. Most of them are probing sort of monojet information. And it has this feature that it kind of alternates between kind of wide angle sensitivity and small angle sensitivity as the beta alternates between sort of the smallest beta option we chose and the largest. So this is what we're referring to as our black box guided. This slide, I think, addresses a couple of the questions that were asked earlier and kind of questions that we had. So one of them is, like was pointed out earlier, if you have this space of EFPs, conceivably you could just kind of check lots of different EFPs and see which one gets the best performance. And that doesn't necessarily guarantee, or it doesn't necessarily tell you that the information that you're missing from something like a CNN is the EFP you chose. But you could potentially, if you just are interested in kind of maximizing performance, so why couldn't you just try lots of different EFPs? And so we did a study where we do that we're referring to as brute force here. So essentially, what we did is started out with our 6 high-level observables, and we just tried every EFP. So you add an EFP and train a neural network and see how well it performs, and then try a different EFP and just iteratively keep trying different EFPs. And then whichever neural network with whichever EFP did the best, that's our new sort of deep neural network. And then we go through all the EFPs again and just try adding in additional ones and sort of iteratively build things up that way. And essentially what you find and kind of what you would expect is that it does really well. But it does really well because you're just trying every combination of EFP. And so the performance is pretty good, but it's just, it's completely inefficient, and it doesn't really tell you what the CNN is learning. It just tells you kind of which collection of EFPs are give you the best performance. And then another question we had that's sort of related to the guided search was, well, if our data is this labeled data set, so we're doing supervised learning, is there any reason that we couldn't just use the ground truth? So couldn't we just use the labels to sort of guide our choices, rather than training a convolutional neural net and then using its predictions as the guide? And so we did a similar thing to our guided search, but rather than using the convolutional neural net predictions as our guide, we just used the actual labels, and we call this kind of our truth guided search. So one thing that's interesting about the truth guided search is it turns out you just can't recover the same performance as you can with either the brute force or the black box guided. So the truth guided version, where you try to let the truth labels tell you where there's this different or similar decision surfaces, it's just impossible to get the same performance as the convolutional neural net, or even just as the 6 high level we used plus the 1 extra EFP. And we think the reason for this probably is that in the case of the truth guided, what you're actually trying to do there is use truth labels even in situations where knowing the truth information is not necessarily a helpful or useful piece of information for a neural network. So there's kind of like a hard limit where if you have your data set, maybe 95% of that data is actually useful for something like a deep neural net to learn the problem. And there's kind of this inherent noise or background noise that's not useful for the task of classification. And so if you're sort of rigidly sticking to, I'm going to let the truth guided information tell me when I've got either a similar or dissimilar ordering, what you're going to end up doing is getting down to a subset of events where there's not really useful information to be learned from it, but it keeps on telling you that there's dissimilar orderings there. And so you keep on including these not particularly useful events in your training. And so that problem is not an issue with something like the black box guided, because in that case, the convolutional neural net has already figured out or has learned which events are not useful and has sort of optimized the problem around those. And we're just trying to piggyback on those optimizations to figure out where this similar and dissimilar orderings are. And so that's why you can train something like a low-level model or a black box model, and then you can, it's more beneficial than trying to just use like the truth labels. And the brute force, like I said, it does work well if all you're concerned about is performance, but the computing time is so much worse than either of the guided searches because you're just trying all the EFPs. And essentially, just to run one pass, one training, one EFP selection with this brute force method, the entire time it takes you to do the black box guided is the same time it takes to do just one pass through brute force. So it's kind of not useful, especially given that with things like deep neural nets, you do a lot of hyperparameter optimization. So it's really unfortunate if you have to train a model that takes 20 times longer, only to then ask the question, well, maybe if I change my learning rate, it'll do better. And so you change your learning rate, now you need to run this model that's 20 times slower than the guided search. So this is kind of our conclusion slide. So in general, there's not really any reason to expect machine learning new methods to get simpler or more interpretable. Most likely they're going to become more complex and more black boxy and more opaque. So methods like this, where you can either find ways to make the talk interpretable, or you can convert information into an interpretable space, are going to become more necessary as we come up with new methods. And in particular, it's really important when dealing especially with things like machine learning in physical sciences, that we understand the models that we're using. So it's not, if you're training sort of just like an image classifier to distinguish between cats and dogs, it's not that important to understand why a neural network does better when doing that task. But in something like distinguishing jets, there's important physical significance to understanding why does this new method do better and what new information is present there. So essentially, what we argue in the paper is that we should avoid using opaque solutions without some kind of context or information to tell us what information is either being gained or lost by using sort of these black box methods. And often these black box methods are useful for telling us how much information is present in a certain problem. But it's important to take a second step to then understand or try to map that information into something interpretable. So essentially, any kind of black box method is that is giving us answers. We shouldn't really view that as having understood the problem if all we've done is train a black box model to make predictions on that. So I'm happy to answer any questions in addition to what we had during the talk.
All right, thank you, Taylor. I think we had a lot of questions during the talk. Still, if there are any follow-up questions, please feel free to unmute.
Hi, I just one other question. So we know that CNNs can have the issue of imbalance. And basically, in your case, you have like mono jets and two jets. So have you looked into the imbalance of those? Because that can bias your loss function, therefore your training, right? Because one and one other can have more pixels, therefore bias the training. Have you looked into that?
For this specific data set, so no. For this, I don't think we did anything. I mean, there's sort of a standard pre-processing for these jet images, but there wasn't. I don't think. Now that I have to think about it now, I don't think we did anything specific to deal with a pixel imbalance like that. But because it was already the better performing of the two, the goal wasn't necessarily to try to improve the CNN by changing the pre-processing. We sort of already knew there was that it was performing better than the high level.
I mean, even you can further improve that if you look into that, right? I mean, you can improve further this if you look into that, because that may be a potential issue that limited your scan.
Yeah, that's true.
Any more questions?
I have a question. So if I understood correctly, so you still need to first make a choice of your linear basis, right, to apply your approach, which is a human decision. And
yes,
so let's say for general problem, it's not guaranteed that you can find it, or may not be obvious that you can find such a basis. Is that correct? Or is there a general recipe that you can always find the proper basis to?
No, yeah. So yeah, you're right. You have to, in some fashion, you have to have a basis that you have to have some kind of existing basis that you can map the information into. And in some sense, in order for it to be interpretable, that would need to exist in some form. Like there needs to exist some kind of interpretable either basis or set of functions that you could interpret them into. But yeah, this method does rely on there existing some kind of something like energy flow polynomials for whatever the problem is that you're trying to solve.
So yeah, let's take this problem as an example. So I want to, so did we learn any physics out of it, or it's just that we express the black box as a parameterization in terms of the EFP? So what physics?
So one of the big potentially physics related pieces of information is just how prominent IRC unsafe observables are. So you can find in the literature where people speculate that the fact that our observables are almost always IRC safe is potentially leaving out lots of useful observables or information. And the fact that this algorithm sort of reliably picks infrared and collinear unsafe information sort of suggests that that's a fruitful place to look.
Okay, thank you.
So the fact that so in the case that when we started with the existing high-level observables, the fact that the first one it picked is sort of sensitive to narrow or small angle behavior is sort of the kind of physics interpretations that we think is kind of the most useful.
Yeah, I mean, the high level observable, we know that it's missing physics, right? For convenience, we dropped all the IRC unsafe information.
Yeah, and so, but I think part of the part of the objective here is that you don't necessarily have to lose that information.
Mm-hmm. Right. So this approach kind of find a way to how to best use of those information.
Right. And so, so one of the goals or one of the potential uses of this is in, say, future dijet monojet classifiers. You could reference this paper and pick the specific energy flow polynomial we used and use it as its own new high-level observable. So if there's a question of, well, what additional high-level observables should we use to improve a classifier that's just using jet substructure and not trying to use something more complicated, we've now picked a useful energy flow polynomial that's worth being sort of the first one that we try.
Okay, I see. Okay, thanks.
Mm-hmm.
Okay, I think we're at a time where it's also pretty late for Taylor, considering he's in France. What I'll do is I'll stop the recording right now. Let's thank Taylor for really an interesting talk. Everybody knows about Zoom, so you know where you can find the clapping hand symbol. And I'll stop the recording. I will leave the room open